So are we ready to go, or should we wait for a minute? I see that there is only one panel of people.
Sir, I think we can wait for one more minute.
Sure, sure. No issues.
Okay, sir, I think we can start now. I'll give you a quick introduction. So good evening, everyone. Thank you for joining. And thank you especially Ramesh sir for joining. So Ramesh sir has interest in molecular radio astronomy and instrumentation and has worked as a radio astronomer at Raman Research Institute for about 3 decades. Has observed and worked with multiple telescopes around the world. Has conducted camp for hands-on research experience in radio astronomy over several summers at Gauribadnur Field Station. He also has interest in communication systems, robotics, automation, and brain-computer interfacing, and to mentor startups to apply principles of physics to find solution to some practical problems. Thank you very much, Ramesh sir, for joining. We can continue now.
Thank you for the lovely introduction. And thanks to Nakshatra for hosting this program. And I'm sure that it will benefit lots of youngsters and make several of them interested in pursuing radio astronomy in general. So my colleagues earlier have introduced you to the beauty of astronomy and radio astronomy and the beautiful objects one sees in the world, that in the universe, that makes you wonder about them and therefore find out more about the subtle aspects of nature. So, and you've also been introduced to how the radiation goes from place to place and the so-called specific intensity, how it behaves as an independent of distance, as long as the source is not resolved. Today, I will take you through a bit about the telescopes themselves, in the sense that on the one hand, you had the waves propagating from distant objects, which is what you want to study. On the other hand, you study them by looking at their images. What connects the two, right? That is a telescope, and in the radio waves, it's a radio telescope. So today we will be seeing, we will get introduced to the basics of radio telescopes first, and then radio telescopes. So what I will do is to share with you the PowerPoint that I've prepared for it. And now and then, if any questions come, which is already not sort of prepared in this PowerPoint, then I'll go to showing whiteboarding or something else. Okay, that's my plan of interacting with you. So I'm going to share now my PowerPoint presentation. So what I would like you to do is to, if you have questions, for example, you could raise your hands and so on and so forth. And I'm hoping that Sagar or someone from Nakshatra team would actually mediate those questions and answers. We can also wait for the questions at the end if that's preferable. Yeah. So are you all able to see the screen?
Yes, sir.
Yes, sir.
Very good. Okay. So let me see now. Okay. So this is going to be an introduction to radio telescope. So my first question would be, who among you have not encountered telescopes before? So those of you who might not have encountered telescopes before, please put up your hands so that, okay. So there are quite a few. All right. Okay. There are at least 5. I'm not sure how many. Someone can make a count if that matters. All right. So now my answer to that would be pretty puzzling to you. We all have encountered telescopes, nothing but our eyes. Okay. So telescope is a device that allows you to look at objects afar. That's the tele part of the word essentially means to look at objects at a distance, telescope, right? But we will understand a little bit about why this afar is important, right? We will get there pretty soon. And man-made telescopes are just artificial eyes. Therefore, much of things that we need to know about telescopes, we can already learn by looking at our own eyes in some detail, right? So at this point, I would like to ask you, any of you can put up your hand and then you can answer. I think that's the way that this interaction can work. Basically, what do you think are the essential components of an eye? Because we all have eyes, right? So we should know about that. And therefore, what do you think are the essential components of the eye, which allows us to have visual perception?
So lens.
Good. Lens. Then?
So we have the pupil that collects the light.
Pupil does not collect the light, but it allows the light to
Yes,
flow.
aperture, a kind of aperture for the telescope.
That's correct. It restricts the aperture. That's absolutely right. So when, for example, in the night time, when it is dark, your pupils dilate so that you can collect more light. When you're walking under the sun, for example, your pupils contract so that the amount of light that falls on the, whatever behind it actually is reduced. The reason being that whatever the detection system that we have is actually very, very sensitive. So that's why this protection is required. So what is the detection system that we have?
Are you referring to rods and the cones?
Yes. So that's called retina. Retina is a kind of a part of a spherical sphere, spherical surface, and in that you have all these dyed molecules which can then pick up particular set of photons, and therefore they detect light. They convert the photons into electricity, and that's the electricity which gets communicated to your brain, which reforms this image and understands and so on and so forth. As you know that, so what sort of imaging happens on the retina? Do you know? How?
Inverted image.
Absolutely. So it's the inverted image of this world that is actually formed at the retina, but then that gets automatically inverted by the brain. So the brain does lots of processing too. So from these, already this discussion, what are the salient components you think of a telescope? A device which will allow you to look afar. Anybody can answer this.
Sir, a lens basically, and an aperture that can collect the light so that it is focused on the lens.
Yeah, so the lens is one component for sure. And then the retina is the next component. The third component is something which will process the image and all that, which is what is the brain, right? So computing device, right? So these are the 3 essential stuff. But there is more to our eyes. We'll come to that. So now let me go to the next slide. So here is a gorgeous presentation of our eyes, right? So you can see in this picture that that's the, do you see the my cursor? Do you all?
Yes, sir.
Yes, sir.
Okay, great. So we have actually two eyes, which allows us to actually form a 3D perception of our world. That's important, right? So it uses trigonometry to do that reconstruction in the brain. And here is the lens. So there is, the first part is called cornea. Unfortunately, here is a nice picture with the illustration, but I'm not sure how clear that is for you guys. Are you able to see? There is cornea, and then there is pupil, and then the iris is the screen. Iris is the thing which allows pupil size to change, right? Depending on the, so that can be controlled by the brain. And then you have the ciliary bodies, which actually control the lens by making it thicker when we want to focus something nearby, and making it thinner when you want to focus something far. So it's a dynamic lens, so it's not, that is, its focal position can be varied. That's the beauty of human eye. Not just human eye, all animal eyes. So here is how the focusing happens. So the light from some object, the two ends, they come, and then it gets focused onto the retina, where the image is formed. Of course, the inverted image is formed. So these three are of course, the essential components. That is the pupil, the lens, retina, and the brain behind it. Pupil is a control of the aperture, basically. That's important if you want to preserve the detection system. This applies to for telescopes as well, as we will see later on. Okay, so that's, any questions at this point? If there's none, let me proceed, right? So now you have this telescope eye, and then let's say that you imagine yourself from, so here is the ecliptic plane, that is plane where Earth is moving around. So you imagine that you're dropping right from afar towards Earth, right? So what do you think would you see? So it may be, I have given you 4 snapshots here. It may look something like this, right? So it goes clockwise. The first picture is on the left top, and then so at this point, as you're falling, you're far away, and if you can see, that is the Earth. My cursor is pointing to the Earth, and then that box is the same box as this one, right? That small box here, that is 1/10 of the. So this is the side of this box is about 10 to the power of 10 meters, and that reduces to 10 to the power of 9 meters. That means you have come closer. This physical, the physical size being the same, that means you have come closer when the distance is expanded. And then you further drop closer to the Earth, and now you have come almost very close to the Earth, right? So looking at these pictures, 4 of them, what would you notice? What would you draw as your conclusions? Can anybody say? What happens as you come from far to closer? What do you notice happening?
Like a detailed view of the Earth.
All right, that is, as you come closer, you are able to get more detailed view. Absolutely correct. Then anything else you notice?
We are getting more light from one particular source, so it appears bright.
So it becomes brighter as you come close.
Tangential rather than circular.
Pardon?
It appears tangential rather than circular.
Okay, you are able to notice slightly deformed shapes and all that stuff. Is that what you mean?
Yeah.
Right. So yeah, that is particular about Earth. You can have a really spherical object. Well, that's true. That goes into saying that we can notice the details of that object when we come closer. Correct? So So that's precisely what happens, in the sense that farther the object, the smaller will be the angular size that it subtends. And also, as the object is farther, it will also be fainter. The reason being, like what yesterday Rajaram told you, that the flux density, or rather the flux, will drop down as 1 over r squared, right? So the flux density will drop down as 1 over r squared as you go further and further. Vice versa, when you come closer and closer, the flux will increase. And you can say that also, that as the objects subtend smaller and smaller angle, what happens is, supposing that you would have noticed in that first 2 pictures, for example, they were both almost same dots, but one of them was less brighter compared to the other, but still it was unresolved, right? Both of them were dots. So so there comes a point where the object gets resolved, or if you imagine that there are 2 neighboring brightness points, as these 2 points go farther and farther from you, at some point they become merged into one. That essentially is the angular resolution limit of the instrument that you are using in order to view it. If you're going to use eye, yes, eye has its own resolution limit, angular resolution limit. And when the object subtends angle less than that, then it will become unresolved. Yesterday, Rajaram talked about this being resolved and unresolved in the context of specific intensity. So you all understand what angular resolution means? Yeah, not necessary that you would have come across this before, that's all right. But there is such an angle limit. How does it come about? We will see now. Okay. So here is a lens, right? And this lens we have, so this lens has optic axis which is perpendicular to the lens, and that is a plane wavefront which is propagating along the normal, that is along the optic axis. That's why it's flat. So when such a wavefront comes and hits the lens, for example, the 2 ends of the wavefront are essentially in phase, right? So when it converges to the focus, it will make the brightest point. Now let's consider another wavefront. Please notice my cursor. So that's a blue wavefront. So this is a black one. So the blue one is actually making a little bit angular offset, and the angle is such that the 2 ends differ by 180 degrees, or lambda by 2. In that case, what happens is the wavefront, when it goes to the focus, this will cancel out the radiation from this end. So effectively similar, not the same extent, but for different portions, different amounts of cancellation will happen. And therefore, the brightness from that direction, even though the incident intensity may remain the same, but that light will actually form less intensity at the focus. So all this radiation within this angle, acceptance angle, will fall into the same focus and form one single focus. Therefore, if there are many objects within this angle, still all of the radiation will be put together and you will get one number at the focal point. So that is the meaning of angular resolution. That is, you do not have the details of object below that resolution. All the details are averaged out. You get a average number. Do you follow? Yeah?
Yes, sir.
All right, great. So that's essentially the classical way of looking at how the resolution element for a single lens is formed. So the important thing to note is that it's directly proportional to the wavelength that you use and inversely proportional to the diameter of the lens. Okay, so understandable, because if the wavelength is larger, that means the angle by which the lambda by 2 difference will happen at the 2 ends will become more. And as the distance becomes larger, right, then also the angle, even for small angular differences, it's very easy for it to make that lambda by 2 differences from at the edges. So that's the reason why that formula is lambda by d. You can also calculate this angle and all that stuff. So basically, the angular resolution is lambda by d. One can also arrive at it from a different point of view, from the uncertainty principle. So you can see that what uncertainty principle says is that the product of the two uncertainties, one is about the photon, the position of the photon and its momentum. The product of the two uncertainties is limited to h, right? So the position uncertainty here is the diameter d. That is, when I receive a photon at the focal point, I wouldn't know where exactly this photon has hit this lens, right? So as the position uncertainty is the diameter, and the angular uncertainty, of course, momentum uncertainty, the magnitude of the momentum for a photon is h by c, and the angular uncertainty therefore is delta alpha. Okay, so this should have been lambda. I have made a mistake. H nu over c or h over lambda. So that's a mistake. So the momentum uncertainty is h nu over lambda, h nu over c or h over lambda, and therefore the product you can solve it, and then you will get that the angular uncertainty will be lambda by d. Yeah. So this is from uncertainty principle as well. Quantum mechanical view also gives you similar results. So the important thing to note is that every focusing element has a certain resolving power or angular resolution limit that's directly related to the ratio of the wavelength to the size of the focusing element. Right. So angular resolution is, of course, lambda by d, and therefore what it says is that as the object becomes, goes further and further, it becomes smaller and smaller. And if you want to see the details in that object at that distance, then I need to use a larger and larger lens, right? So that's one of the fundamental requirements of why we need telescopes, right? So that's because the natural, of course, another is of course frequency and so on and so forth. But the primary reason is that the natural telescope that we have allows us to see only objects up to, because it's limited by the size and therefore the resolution. Therefore, beyond a point, we will not be able to see the details in objects, and therefore we can't distinguish them. We will see them all as one, even though it's a group of set of say stars, for example. So as we saw, further an object, it also gets fainter as 1 over r squared, because the power gets distributed over larger and larger surface area. But if I make my lens larger and larger, because it has larger, it will collect photons from over larger area from this sphere, right? Spherical surface. It will intercept larger portion of that photons, which means that it will become more sensitive. So therefore, a larger telescope or a lens is also required if you want it to become more sensitive. So there are two reasons. Number one, when you want to see the details of the objects, then you need resolution, and therefore the size has to increase. And the number two is that if you want to go fainter, if you want to detect fainter objects, then also you need to have larger size, and therefore you need to construct larger telescopes. So that's the primary reason for why we need telescopes, bigger and bigger and bigger and bigger, right? So the third aspect about telescopes is that right now you are looking at the screen in whatever device that you have. So you are looking at the screen. The screen is nothing but a brightness distribution. There are black points, white points, and so on and so forth. but all of them are not forming in your optical, in your retina. They form into, they are all focused at different points. That's how you're able to see this as an image. The sense image is brightness distribution over n number of pixels, the pixel element being the resolution element of the display, right? If you, for example, if you take a picture and if you keep on expanding the picture, at some point you will start seeing pixels, right? That the intensity across the entire pixel is the same. There is only one number there, right? So that is the resolution element of the display. In this case, you may have a resolution element of 1,000,000 pixels or something like that, 1,000 by 1,000 or 800 by 1,000, 200 or whatever. So that gives you the number of pixels. That is, each pixel can carry separate information. So by combining all these pixels together, we make an image. Same way, the sky image is formed by having simultaneous measurements of multiple pixels across an area, angular area, which is called the field of view. So that is what is important is that just like in the case of individual, in the display case, where individual pixel has one amount of information, same way in the case of an image, in the field of view has many resolution elements, angular resolution elements. In each angular resolution element position, you get only one number, or if it is frequency domain, yes, you will have series of numbers across the frequency, but positionally only at one position, right? So you don't have details within that pixel. But the image is made of multiple pixels all arranged together, right? So, and when we say field of view, we mean that all those independent information is simultaneously measured. That's the idea. Of course, then if I want to really make a large image, I can put this image, my field of view, multiple times, each individual time taking, so that's time division multiplexing, the sense that you can take some certain amount of time, image this part, certain amount of time, image the next part, and then you can combine them together, just like panoramic view of a camera image that you make, right? But that's not simultaneous, right? So you spend more and more time when you want to combine many such pixel, facets together. Okay, so now I'd like someone to estimate the resolution of the eye. Possible? Just lambda by d, right? What would be the lambda that you would use? Anyone?
Wavelength of physical spectrum.
Pardon?
Wavelength of physical spectrum.
Yeah. Rough number. I mean, what would be the wavelength? Center, for example, of the visible spectrum. Would you say 500 nanometers, 5,000 angstrom, 0.5 micron? Would
Yes.
that be okay?
Yeah.
Yeah. So take 0.5 micron. And what is the diameter of the pupil?
1 mm, 2 mm.
Take 2 mm, for example. It can expand to 3 mm in the night and all that. But anyway, take 2 mm. And then find out what is lambda by d. What you'll get is, of course, you have to convert them all into same units. And then that will be in radians. Convert that into degrees or arc minutes, whatever is relevant. And tell me. Just a ratio and unit conversion. So, yeah, I think any one of you can do and let me know. I'll just wait. Is it okay?
Sir, is it 0.014 degrees?
Yeah, multiply that by 3,600 and tell me what in. Oh, sorry. Multiply by 60, then tell me what is in arc minutes.
Is it 0.9 arc seconds?
0.9 arc seconds? No. More likely 0.9 arc minute you would have got.
0.859 arc minute.
Yeah, so roughly about an arc, 1 arc minute. Yeah, which means that our eye can distinguish as long as 2 points of light are separated by 1 arc minute. But the moment it goes below that, we will not be able to see them as 2 individual light sources, but it will appear to be as 1 light source to our eye. Yeah, so that's the resolution limit of the eye. And there are many other things which have similar resolution limits. For example, okay, that we'll come back to this resolution for other things. What is the field of view of eye, you think? That is simultaneously over what size? Angular size, horizontal, vertical. My eye
Probably
is
150 degrees.
150 degrees. No. There is a peripheral vision, there is central vision. Okay, so don't include peripheral vision. Peripheral vision, of course, is broader, but it has it's not accurate in the sense that the brain uses it for certain purposes, and then your central vision will actually go to that whenever there is a trigger, right? So central vision will be more or less 20 degrees to 30 degrees or something like that. Okay, it's like, for example, one good way to estimate that would be, if suppose you have your screen in front of you, what is the distance that you are in and the entire screen is visible to you, right? So roughly speaking, the width of the screen and the distance to the screen is more or less the same. That is about 60 degrees. Would you agree?
Is it 60 degrees? More like the width of a fan.
Of the laptop screen. That's the reason why they don't make it much bigger and then make you to sit close by, right? These are all ergonomically designed. So it is true that about 30 degrees, 60, 30 plus or minus 30. Maybe you were right at the beginning. You said 100 and something. Okay, so 60 degrees. That itself is seems pretty large actually. It's more, I would say, about 30 or 40 degrees by 40 degrees is the area where the central vision applies. Anyway, so that's a field of view. What it means is that, okay, so we said 1 arc minute is the resolution, and let's say 60 degrees is the field of view, 60 degree by 60 degree, right? So how many pixels do you think on the retina that this image is forming? This, we are only talking about the central vision. 1 arc minute is the resolution, 60 degrees is the one side of the field of view. How many pixels? How many resolution elements of information that we are registering in our eye and in our retina? Every, you know that there is persistence of vision and all that. Every 20 milliseconds it gets flushed out, right? So so that's something like, say, 50 hertz or 100 hertz rate that this information is being recorded. So what do you think is the number of pixels on each, this n by m or whatever, that number? Someone tell me.
600 megapixel.
That's right. So it's more like 10,000. See, 3,600 by 3,600, right? If it is 60 degrees, then you have 3,600 pixels, assuming vertical. Yes, it's true that eye is much more wider compared to the height. We don't record that much information. That and all, that's because of evolution, right? All these hunter-gatherers, what do you want to see and all that stuff. So, yeah, so, but imagining that it's to be squarish, so you can say that it is 3,600 by 4,000 by 4,000 is how much? That is 16 megapixels, is it? Yeah, right. So each one of us natively are equipped with a 16 megapixel camera, which is actually pretty good in terms of its detection capacity. So how sensitive you think our eyes are? What is it that it can see? How faint can it see? That's sensitivity.
You mean in the luminosity value? Like how many lumens?
See, we have said that it is 0.5 micron, right? So we are only talking about sensitivity in the 0.5 micron range. I mean, whatever the bandwidth it has, that's okay. But it can, that bandwidth, it integrates over that bandwidth light, and then it is able to see up to a certain faintness. Beyond that, it's not able to see, right? So, I mean, this level of faintness, you guys may not be so much aware if you are not an astronomer. So basically, yesterday, Rajaram mentioned about the magnitude scale, just like flux scale in Jansky, magnitude scale in its magnitudes. That is what is used by optical astronomers. In that scale, our eye can see up to about 6th magnitude or 7th magnitude star. Another way of saying that is, okay, there is beautiful cloudless night, cloudless as well as moonless, and then you lie down and look up in the sky, the kind of stars that you can see, the faintest star that you can see, of course, from person to person it varies, but roughly it's about 6th magnitude to 7th magnitude. And when you convert 6th magnitude or 7th magnitude optical light into Jansky, you'd be surprised to see that it's about 5 Jansky. It's the same limit. So radio astronomers and optical astronomers, in terms of the energy scales that they're talking about, is eyesight is a kind of limit. It just happens to be so, but it's quite surprising that it's like that, right? So, okay, so now what have we so far learned? We have learned about angular resolution and the field of view and sensitivity, right? And it is in order to, field of view is, we'll come back to this field of view a little later because it applies to radio astronomy quite severely. So we'll come to that later. But both angular resolution and sensitivity, if you want to have better angular resolution and better sensitivity and so on and so forth, then obviously you need to have larger and larger size of this focusing element. So as we said that, I mean, from the eye we learned that there is this lens that's required. Pupil is, okay, it's not that important, but anyway, that is to restrict the area over which the light is accepted by the lens. Now, the lens and then the detecting system and then the processing system. These are the 3 important things that we require if you want to make an imaging or light recording device, right? Which is what a telescope is. And we also see that the constraints by angular resolution and sensitivity require that you have to make larger and larger telescope if you want to see finer and finer details and look at fainter and fainter objects. So then the next question aspect that we will discuss now, what's the time? How are we doing? Me. Okay, it's about, we have another 1 hour, isn't it?
Yes, sir. Yes, sir.
All right. So if there are any questions, somebody has raised their hand.
Asad is asking a question. Yeah, Asad, you can unmute.
Hello.
Yeah, tell me.
Hello, am I audible?
Yes.
Good evening, sir. So there is a small doubt regarding the overall idea of telescope. Okay, so this telescope, what you have told about, what you have told us up until now. So these apply to all the telescopes or just like the radio telescopes? Because in certain telescopes, I have learned that in certain telescopes there aren't imaging technologies. Like some telescope don't have any imaging capability.
Yeah. So
yeah, that's the overall question.
Well, so that your imaging capability is to do with the field of view, right? Well, if you are, we are not quite discussing about X-ray telescopes because there are techniques, different techniques that are adopted to construct telescopes at different wavelengths and frequencies for a variety of reasons. Because here, so far whatever I have discussed, the light has to be refracted. Now, that refraction doesn't happen for once the wavelength becomes too short. It doesn't see these atoms and the electron clouds and so on and so forth. It just simply goes through. So refraction becomes difficult. So it is, then you have to, the grazing angle diffraction and so on and so forth. That's what you have to do. Then there are other issues of constructing such a telescope. So I'm not, so it is not true that for the entire band, that is from radio to X-ray, you can construct all the telescopes in the same way. No. Okay. There is a lot of similarity between optical telescopes and radio telescopes, but there are also differences which we'll come to. The main area of difference is, of course, the field of view. We will discuss about that little later, in more detail. But these aspects, that is both angular resolution and sensitivity, that applies to all these refracting or reflecting telescopes.
All right. So, like overall, like in different wavelength, they require we require different kind of telescopes. Like not all of them have the same idea.
Yes, the method of how do you construct the telescope, right? That can change quite dramatically.
Okay. Okay, sir. Got it. Thank you.
Yeah, that is to do with the nature of the photons themselves. So, and then how you can collect them, bring them together to a central point and process them and all that stuff. So people adopt different methods to both sense those photons and then use it to judge the direction in which it comes and all that stuff.
Okay. All right, sir. Thank you.
Sir, there is a question by Likita.
Yeah.
Probably she was asking regarding the focusing aspect of a lens. How does raise a different incident angle focus at the same point?
Okay, so that is, one has to then go into the details of a lens. But basically, what happens is the following. So what do you want to do? You want to, well, what comes in is a plane wavefront, right? So this plane wavefront, the lens has to, what it has to do is to, after this plane wavefront passes through the lens, that wavefront should no longer be planar, but it should be a part of a sphere. Then if it is a spherical wavefront, you can imagine that it has to go to a point, correct?
Yes, sir.
Yeah. So the lens, what it does is precisely does this job of converting a plane wavefront into a part of a spherical wavefront. How does it do that? It's by delaying different parts of the wavefront by different amounts. You can see that, no? Okay, let me.
Yes, sir. For example, in the middle, it is delaying a lot, but in the edges, it is delaying less.
Yes, absolutely.
For a convex lens.
Yeah. So that's why. So the propagation speed inside a medium of light is lesser than the free space, and therefore, as it the lens is thicker at the middle, so it delays it more, and as it becomes thinner, of course, you have to design the shape and all that. There is lots of things involved. In the sense, there is refraction also. So the refraction changes the length over which it is traveling inside the material. So you have to combine all of them to design the lens. But the principle is this, that you delay by sufficient amounts so that over the diameter of the lens, as it passes a plane wavefront from one end to the other, as it passes, it becomes part of the sphere, spherical wavefront. And Likita, whoever asked this question, do you think it's possible or not?
Possible.
By proper design of this thickness, by varying the thing, if you have to get the right curvature. The planar wavefront is correctly curved. Is that possible?
Yes.
Yeah? You're convinced, no?
Yes, sir.
Okay, good. So, any other questions? All right. So, shall I move over to the next aspect, that is mounting? Yeah?
Yes, sir.
So, look at our eyes again. Why I'm going back to the eye is that it is a visual device which allows us to track objects, to see objects, to do lots of things, right? Therefore, we must learn from this as to what is its what a telescope requires, right? So the eye is mounted in the eyeball. Now you can turn the eyeball up and down and so on and so forth quickly. Maybe not me, but someone else can do it much more easily. And then when you want to see an object moving, you are looking here and you can directly go there, right? So over a smaller angle, your eyeball can move very fast. That's mounted. That's mounting. In the sense that the ability to move from one point in the angular space to another point. If you can move, then that's tracking. So that's what we use to track an object, an animal or a bird or whatever, right? We can follow with our eye. We also have this neck mounting, in the sense that the neck allows us to move this way, and so on and so forth. And then the whole body itself can move. So therefore, we can follow an object all around, for example, right? So that's the kind of mounting that nature has provided. But of course, the telescopes are not exactly mounted. They are mounted slightly differently, right? So we will look at how the telescopes are to be mounted. But then, why do we need to track? Only if we need to track, that we have to mount the telescope, move the telescope. Mounting allows the telescope to move its optic axis or radio axis from one point to another in the. So there is this thing called celestial sphere, in the sense, or the sky, right? Our sky, you can imagine that to be a sphere of unit radius, whatever the radius, the unit of the radius can be in kilometers, megaparsec, whatever, right? But basically, it's a unit radius part of a sphere in which all these objects appear at various locations. So when you want to go from one source to another source, yes, you have to move an angle. So that is one basic requirement. That is because there are objects, plenty of objects on the sky. From wanting to go from one point to another, one source to another, I have to move. So I have to have the capacity to move. Therefore, mount is necessary. But are these objects located in the same position all the time? Celestial objects. Are they constant?
No, sir.
Why not? See, my argument is the following, right? These objects are very far from us, isn't it?
Yes, sir.
If they're so far, if they're moving a little bit here and there and all that, I will not be able to make out, because it will take long time for it to make substantial angular positional change. Therefore, I would say that at any short time scales, that is a day or a couple of days or week or month or whatever, these objects should be essentially at the same positions. Objects I'm talking about really far away objects, right? They cannot change their positions, because position change means that angle change, but because they are so far away, their linear speeds, whatever speeds that they're moving, cannot be so much that they will make substantial positional change, angular positional change, in my view. Therefore, they must be constant. No? What do you think? Anyone can answer.
Yes, sir, but the apparent position changes because the Earth rotates.
Right. That's the reason why they are called constellations, right? In the sense, there are visible patterns that are formed by objects in the sky, on the sky. That pattern doesn't change at all, isn't it? The reason why those actually minute changes do happen, but anyway, not that we can easily make out over thousands of years. The reason why those constellations don't change their shapes is because these objects are really, really far from us, right? So there are these constellations, and that's the reason why these constellations are used. In the backdrop of these constellations, the planets move. Planets move very fast, right? Especially the inner planets, they move fast. Outer planets also move over a longer period of time. So that's why the planets are called wanderers, because they wander in the sky. Other things are fixed. In that fixed firmament, right? Things move, the wanderers move. That's the idea of celestial sphere. But as you said, the Earth moves, and because of which those objects are not stationary in our sky, because we are rotating, we are moving along with the Earth, and therefore, so we need to track. Even if you are interested in one particular object, you have to keep changing your look direction, because that object is moving in your sky. That reason why the object is moving in the sky is because the Earth is rotating, right? So, yeah, that's essentially what I said. That now the next question that arises is that, yeah, this, let's say that the celestial objects move. If they move because of Earth is rotating, right? So what would be the periodicity of their motion? Can somebody say? Would it be a day or half a day, or what would it be? The sense that periodicity means they come back to the same spot, after that period. They keep moving because it's only Earth is rotating now. They keep moving and then they come back to the same spot after a certain period of time. That's that period of that is a periodicity. So my question is, these celestial objects, their periodicity, would it be a day?
Not exactly one day, sir.
Who is that? Avantika. Why do you say that it is not exactly one day?
Because the Earth is also revolving around the sun in its orbit.
Good. So that's so what Avantika said is described in this picture. You can see that here is the Earth. Here is after one rotation, self-rotation of the Earth, pointing to the same object, which is here. This is the stars, right? So the Earth in this position is here, and by the time that it has rotated around and come back to look in the same direction where these distant stars are, it has moved, right? Yeah, but it is looking in the same direction. So there is a certain amount of time. Now let's look at what would be one day. One day is solar day, right? So the Earth is here, for example, and then it is looking into sun, and then it is rotating and then come back here. When it is looking in this direction, it will be looking here in this direction, right? But then it has to move a little more angle in order to look at sun. That's because in that time, because of its orbital motion, it has moved to a different point with respect to sun. Sun is nearby, and therefore this small distance change, the position of the Earth, actually makes a larger angular change, right? So therefore, what would you say? One solar day would be shorter than one stellar day or the sidereal day, or it would be longer?
It is longer.
Yeah. Do you know longer by how much?
Roughly 4 minutes or 3 minutes. Something.
So what, you guys are all some amateur astronomers or something? So I don't need to be talking about all this. Good. So that's important to understand, that the periodicity of celestial objects, that is distant stars, is not the same as one day, but slightly smaller, shorter than a day. So we call that as sidereal day. Astronomers call it a sidereal day. So we know that yes, the objects in the sky are moving. They are moving almost like one day, but not exactly one day, and therefore we have to be able to follow it properly if you want to track the source, right? So you have, because these objects are in a two-dimensional spherical surface, you need two angular coordinates. So you can, the angular spherical, because the distance is, we have taken as unit. That unit can be anything that we want, because these objects are really far away, right? So the distance falls up out of this whole thing. Basically, to point to a particular direction, you need two angles, one about one axis and the other about another axis, which is perpendicular to the earlier axis, right? So that's essentially, you need two axes, that's for sure. Now the question is, how, if I need a system to point to these objects with two axes, can I do something with these two axes in such a way that it benefits me in some way, right? Yes, that's what essentially the two coordinate systems, that is mounting methods that astronomers use exploit this thing in order to gain some advantage. For example, if one of these axes is aligned to the Earth's rotation axis, which is what I have tried to. So let me see if I can do this. Okay, if I stop sharing, I'll be pinned, and therefore I can come back to start sharing. Just one moment, I'll stop it. But I'm not pinned. Can I request Sagar to pin me so that, thank you. All right, so you guys see?
Yes, sir.
Yes, sir.
So this is the rotation axis of the Earth, right? And then,
Yes.
maybe, okay. There is this inversion that I have not bothered about anyway. So this is the rotation of the axis of the Earth. One axis is always made parallel to this rotation axis. The other axis is perpendicular to that, right? So this kind of a support system, mount system, is called equatorial mount. But you can see that this in the equator, for example, this is just this axis is parallel to this axis, which means that about this axis the object can move or rotate like this, right? The telescope. Whereas here it is parallel to this axis, but see how much it is making an angle to the local, either tangent to the circular part or to the normal, local normal, right? This is making wider and wider angle to the local normal. I mean, or
hello, sir.
Yeah.
Yeah. Where exactly are you pointing? Because
yeah, my cursor is not visible to you.
No, no, sir. You are not sharing screen, no, so it won't be visible. It would be.
Okay. Okay. I'm sorry then. All right. So then I will use my finger to point, right?
Yeah, that would be good.
Sorry. Okay. So this is the rotation axis of the Earth. This is the axis, one of the axes about which the telescope can rotate like that. And the other axis is perpendicular to this. It can rotate like that. So this axis is made parallel. You can clearly see that there are multiple ways of supporting it stably. But what happens as you go at larger and larger latitudes is that this angle becomes very, from the local normal will be like that. This angle makes wide angles, basically 45 degrees and so on and so forth. And their mounting becomes an issue, especially for larger and larger telescopes. But yes, the advantage of this thing, let me go back to sharing the screen.
So what does it mean by local normal?
Local normal is the gravity direction locally.
Oh, okay, okay.
Right. If you drop an object, it doesn't go at an angle, does it? Not in
no,
my
sir.
case.
Yeah, I got that.
Yeah, that direction is people. I mean, all the civil engineers use this plumb line and all that. No.
Yes,
yeah.
sir.
That is the local normal. Yeah. So if one, so yeah, we'll come to this. I mean, I have a picture which will show this better also. Anyway, so basically there are two axes. One axis we can align it to the Earth's rotation axis. What is the advantage? The advantage is that if you want, once you have pointed to the object, to track it, all that you have to do is to rotate about this, compensate for the Earth's rotation. Earth is a big object, right? So it rotates at a constant speed. So you have to just compensate for that constant speed, and that's it. Any DC motor would do. So it was an easy thing to do. That's the reason why early astronomers preferred mounting with equatorial mount, because you don't need to, there is nothing to calculate, nothing to compensate. It's very easy. Then with a guide telescope, you can very minute adjustments you can do. So that's essentially how equatorial mount became very popular earlier. But then there are two problems with the equatorial mount. The one problem, as I said, is about the balancing of, for small telescopes, it doesn't matter. It's possible. It's no problem. right? That's it. The earlier times they used small telescopes, and therefore there were no issues. But the moment you make the telescopes larger and larger, counterbalancing of the weight so that center of mass comes in the proper alignment, and then there is enough support that at that point, those becomes issues. So big telescopes become a problem, number one. Number two is that early astronomers were only looking at, let's say, distant objects, stars. Then this tracking that is compensating for the Earth's rotation is simple. But if you want to look at, even outer planets, more or less over a day, they don't change much in their declination or something like that. So you can say that, okay, even outer planets, I can use the same technique. But the moment you go to, say, inner planets or comets and so on, so which are moving very fast on the sky, and their tracks are very different from, because the tracks are not formed because of the motion of the Earth's rotation. Their tracks are formed because their own peculiar motion, right? So if you want to track such objects, equatorial mount is no good, in the sense that you have to compute their instantaneous positions in your sky view, and then adjust both. In the case of equatorial mount, one angle is called hour angle, that is right ascension direction, hour angle. Another is declination angle. I mean, I presume that you guys know about these angles. If you don't know, we'll see. Anybody has confusion about what this so-called equatorial coordinates? Okay, briefly it is like this. That is, Earth's axis is there. This is the equator, which is perpendicular plane to the Earth's axis, right? So the equatorial coordinate system is same as our longitude, latitude projected onto the skies. So the latitude would correspond to the declinations, and the longitudes would correspond to our angle. Is that understood?
Yes, sir.
Yes, sir.
Yeah, so that is the equatorial coordinate system. So in the equatorial coordinate system, so we are having in the same as the Earth's rotation axis, there is an axis. So you will describe the positioning of the object along about that axis. Another is perpendicular to that. So, but if it is not, if the tracking, that is, if the object's motion is not determined by only Earth's rotation, then it is actually forming a complex track on your sky. And to follow that, you have to both move in declination as well as in hour angle. So you have no easy way of moving at a constant rate and stuff like that, right? So therefore, it's no longer beneficial once the objects are not really celestial objects, right? In the sense, faraway objects. The other way of mounting, again, which is beneficial, is structurally it's beneficial because you can take one. So after all, I have a hemisphere, a dome, half dome, and I want to point to different object points on this dome. Then I will make my local normal to be one axis, which means I can move around that local normal, right? And then I'll make another axis which is perpendicular to the local normal, like this, like a T. So this can rotate up and down like that. So this can be rotating like this. You guys are seeing me?
Yes, sir.
And then you can rotate like that. So these are the advantage of this is that the center of mass of the entire system is well balanced through the certainly one axis. The other axis you can easily counterbalance it. So therefore, the structurally it becomes pretty easy and stable. So that's the reason why this is in the modern days it's preferred. Of course, this what it means is that in this coordinate system, the constant declination circles will actually correspond to various. I mean, you have to both move azimuth as well as elevation in order to make the track, right? And the amount of motion is not non-linear now, because one will be a cos theta component, another will be a sin theta component of that actual track, and that is constant. But these two are no longer constant because it's sin theta cos theta stuff. So it is it's non-linear, and therefore you have to be able to move at different rates at different times. So this requires computation and all that stuff. In the earlier times, when there were no computers, again, nobody preferred azimuth axis, alt-azimuth mount, obviously. But then nowadays, that's the most common mount. Then there are instruments called transit instruments. This is just for the, for completeness sake, I am mentioning it, wherein you only provide one axis motion. You don't provide the other axis motion. This axis is perpendicular to the, so that you can track, you can see the entire great meridian, local great meridian in your, that is in your location, the zenith, the north pole and south pole. That's great circle that passes through these 3 points. You should be able to follow that. That's all. So that means that's a plane. This axis is perpendicular to, the normal, aligned to the normal of the plane. So once you do that, then you can only look at the objects anytime along this great meridian. But because the Earth is rotating, it will bring different objects at different times to cross this great meridian. So if you have a finite field of view, then as the object is moving across your field of view, you can observe that object. It is time limited, but there are certain situations where it is advantageous. So that is just to complete the picture of mounts. Okay. So here is the picture of the equatorial mount. You can see that, right? So this is the right ascension axis. Okay. So this is to compensate for the rotation of the Earth. They are calling it as rotation axis of the, okay, that's right. So it is at a particular place, wherever that is, the local latitude is 48 degrees, the guy is mounted like that. And then this is rotatable about this axis. Okay. So that is this whole thing. I don't know how to say that. So this T is rotatable like that. So that is to track all the declination from northern to southern. So that's essentially, this is an equatorial mounted. It's called the German equatorial mount. Okay. So this is the alt-azimuth mount. It's actually called Dobsonian mount because the guy Dobson was the one who popularized it, but it's basically an alt-azimuth mounted Newtonian telescope, optical telescope. You can see the side Newtonian. So basically the way this works is that this is the azimuth axis, right? So this is like a gun turret, right? In a gun turret, you can rotate it about the axis perpendicular that is along the local normal, and the other axis is perpendicular to that. You can move up and down like that. So that's essentially, so therefore you have two angles and you can track, point to any object in a hemisphere. Then to track means that you have successive points in that hemisphere. Whatever the track is, you compute them and then go from one point to another. That's essentially tracking. But that computation requires a computer in this case. There are expert optical viewing guys who actually will compensate for it in their mind and then will move it accordingly. That's because they're having this feedback visually and then they keep bringing back the object to the crosshair or something like that. So, but otherwise, it is a bit challenging, right? That is, we have to do it without a computer tracking a source for a long time. That becomes extremely tough. All right, so yeah, so basically what I have said all these things before, that is, mount can help a telescope to point any object on the sky, but then celestial sources are not static and therefore they due to its rotation, and therefore one has to compensate for that. This is easily done by equatorial mount simply by rotating about one axis, but in an alt-azimuth mount, these two rates become different and they are non-linear, and therefore one has to have the benefit of computers. But alt-azimuth mount is more, structurally more stable and it's easier to construct. Therefore, more and more. Also, to follow objects which are planets and comets, in both cases, you need to move about both the axes simultaneously. So it's no longer one axis becomes static. It's not like that. So therefore, of course, for that also you need computers. And then for these reasons, more modern telescopes have adopted ultra-azimuth mount. Now, what are we doing with time? Okay, 20 minutes, good. Okay, so to stay on a celestial source, one needs to compensate for Earth's rotation. That's what we saw. But is that enough? No, actually. The reason for that is that, so there's the Earth's rotation about an axis, but this axis itself is not stable. It's not stable for two reasons. One is that, so it's a gyroscopic effect because it's going around the sun, and this axis is tilted with respect to the ecliptic, and it is self-rotating. So there is a torque that applies onto this object, and that because of the sun, and that is actually making it to wobble, right? So this axis is not pointing to one direction, just like your top spinning. It wobbles about a particular direction. So that wobble, likewise, this spin axis wobbles about the mean axis, mean direction. So that wobble is caused by sun. That's one part. That is a long period wobble, and that's called precession. In addition to that, the Earth has its neighbor, which is the moon, and the moon is also orbiting around the Earth, but this orbit is not also aligned to the equatorial plane. It is slightly away, and therefore Earth is making the moon to also, that moon's self-rotation axis to precess, and that precesses rather the, basically this orbital direction precesses, and that is precessing at 18.6 years, and the corresponding tug, equal and opposite force, which is applied onto the Earth, and that is making this wobble internally to wobble, and that's called nutation. Okay, so is that understandable? So here is a pictorial view of the same. Basically, here is the axis of rotation of the Earth, and it is moving like this about the sun, but it is not pointing to the same constant direction. That's what has been shown down here. So it is precessing about this nominal direction. The Earth's axis never points to this direction, but then it goes around that direction. The amplitude of this wobble is about 2 degrees. Have I not mentioned it? This amplitude is, I think, or yeah, I think it's about 2 degrees. And then this internally, you can see that there is some sort of a jitter. It is going around, but at the same time, inside that, it is actually jittering. That is the wobble caused by moon, and that's called nutation. That is inside, wobble inside wobble, right? So that's called nod. That's why nutate is to nod. So it's called nodding. So to get, therefore, because our axis itself is not stable, therefore what happens to the objects on the sky is that they dance like that, right? They dance like that. So the positions of the objects is not going to be remaining constant. You need to correct for, I mean, if I take a snapshot of the sky, celestial objects on one night, they're constant position, but they are not going to register in the same place, and they will be moving around like that. And I need to, whenever I have to look at them, I need to compensate for all those errors that have happened, and then remap to the present day, how they are going to look, because I have changed the direction of my rotation, basically. So that's essentially the compensations for precession and nutation that one has to do in order to compute, to point to the celestial object and then track them, right? So the way to point to celestial sources is like this. First, we talked about the equatorial coordinates, that is how the celestial sphere doesn't rotate. Only the R angle coordinates is rotating. Equatorial, the celestial sphere remains constant, in which all these objects are located. But they are not, the celestial sphere is still defined with respect to the Earth's rotation axis. And therefore, these objects will do this wobbling and precessing, nutating and all that stuff on this hemisphere. So you present their positions at one epoch. One epoch is one point in time, right? So at that time, on that day, at particular time, precise to 0 seconds or whatever, where were these positions in that coordinate system? That is what is given as the at a given epoch, the coordinates of an object as a given epoch. So then from that time, so basically astronomers would use something like J2000, J1950, all that stuff, right? So B1950, J2000 is the code name, right? B1950 and all that. So that particular coordinate is, that is, those were the positions on that particular day, January 1st, whatever, 1950 and so on, at 0 midnight at Greenwich GMT, 0 GMT and all that stuff. So then, given that the coordinates, they were the positions at that, on that day, in my coordinate, how would it look? My coordinate has become different because my my actual rotation axis has shifted, right? So this is a simple spherical coordinate transformation from that sphere to my current sphere. My current sphere's position, I mean the actual direction of my rotation axis can be determined from something. So the current position, current direction of the rotation axis is to be computed using the precession and nutation, and then accordingly you have to do the transformation of those positions to current coordinates. That's essentially what precession and nutation corrections do. So you do that. So, and you have to do it precise to the current moment or even ahead. You can compute for the next 5 seconds later or 10 seconds later and so on and so forth. Then you have computed that positions. Then that is your current celestial coordinate system where these objects are. From that current celestial coordinates, you have to, given the IST, longitude, latitude, Julian days is required in order to do the correction to the current coordinate system, current epoch. Once you do that, then you have to convert that into the local altizimuth coordinate system. So that's the next coordinate conversion. Once you do that, you know where to point your telescope at that time. 5 seconds ahead you have computed. You know that when the time IST crosses that particular instant, you know where in azimuth your telescope should be located, where in elevation your telescope should be located. That's it. Then for like that, every 10 milliseconds or 100 milliseconds ahead, you can keep on computing and then keep pointing to the newer and newer azimuth and elevation coordinates, and then you will be tracking the source on the sky. Is that clear? Understood? Hello?
Yes, sir.
Yes, sir.
That's understandable, no? Not a complication, right? So essentially, this is what is required in order to track a source. If you want to track a source, okay, then the question can be, okay, if it is celestial source, yes, we have this coordinates in a particular epoch, and then we get, what about planets, for example? Planets are not faraway objects, and therefore they cannot be put on the celestial sphere, right? Because they are wanderers, so they will be making a track. So then what is, you have to go through ephemeris where for every day, they're apparent at a particular time, 0 GMT and all that, their apparent or apparent deck for that particular day will be given every day, right? So you can use that, and you can, if you want, further interpolate and all that stuff, then you can get the current apparent array and apparent deck, which is what is the equatorial coordinate system as of now. Then you can convert the same thing to azimuth and elevation coordinate system, and then continuously follow it up, right? That's essentially how we do the tracking. you can ask is, well, actually speaking, there is something called telescope pointing model, in the sense that in all these discussions so far of the coordinate systems and conversion and all that, one has assumed that these are exact coordinates. In the sense, we say that, oh, you have local normal and then axis perpendicular to that. But when you want to construct physically, right, the local normal, to what degree, to what accuracy is it local normal? That's a challenge, right? So it will not be exactly local normal. Maybe it is 1 degree or plus or minus 1 degree this way, that way. It may be off. Then what happens? So it's no longer local normal, no? And then, so that goes into this so-called pointing model. And then this other axis, which is elevation axis, is supposed to be like this, which is perpendicular. But everything, when you want to construct physically, it becomes an issue. So it may be tilted like this. Okay. So then, so these two coordinates no longer are orthogonal to each other. Therefore, there is a there are consequences because of that. In the sense that there will be some cone of avoidance and stuff like that will come, and also there will be some mixing of the two axes will happen. So you have to compensate for that in order to. So the exact way that we compute all the coordinates conversion happens is that from the epoch to the current epoch, from the current epoch to the ideal altazimuth coordinate system. Then from the ideal altazimuth coordinate system, we go to the actual coordinate system by applying this pointing model, correcting for the pointing errors due to the construction of the practical device. Those are things. There is one more thing which I have not put down, is that we are below the Earth's atmosphere, optical or radio guys, and so this thin layer of atmosphere is going to refract the wavefront. So the wavefront is not exactly propagating along straight line; it is bent, it's curved, right? So a source, even though actually it is there, it will look slightly in a different position. You have to correct for the refraction, actually. So that is another aspect of tracking the source. Especially these are important for bigger and bigger telescopes, because your resolution element has become finer and finer, and therefore you will not be able to, you will easily miss the source if you don't correct for these things. All right, so then, yeah, so this is sort of summary of what so far we have done. So we have seen angular resolution, field of view, and sensitivity of telescopes, how its rotation causes celestial objects to move on our sky, and then what is the difference between solar and stellar times, because I mean solar and sidereal times, and then different types of mounts that people use for telescopes and their advantages, disadvantages comparison. And then how do we, so it's not just the Earth's rotation that we need to worry about. The wobbling of the rotation axis also happens at 2 stages. One, the long-term wobble, another is the nodding part, right? Those also have to be compensated if we want to point to the source correctly, right? And therefore that follows spherical trigonometric transformations and all that. So here is your first assignment, basically. Write a Python code to convert celestial coordinates, that is J2000 for example, to the local coordinates, hour angle and declination code, equatorial coordinate system, local equatorial coordinate system, which is hour angle and declination. That is celestial equatorial coordinates, which is constant alpha, and that is right ascension declination. So from the right ascension and declination, you convert to hour angle and declination using the current epoch, local latitude, local longitude, IST, wherever you are, that's fine. So, but I mean, these quantities should not be fixed. You should be able to give whatever correct values for different positions. Then you should be able to calculate, that is precision and nutation corrections to be applied, and to the current epoch. From the given epoch or a deck, you are transforming to the current apparent array, apparent disk, and then convert that to current apparent array, okay, or hour angle basically, because time is also, local time is involved already. So the hour angle and declination, and then you convert that into altitude and azimuth. That's the next part, the extension or another code, right? So can you guys write the code like that? You can get the resources for this on the web. Otherwise, we can help you with
I will try, sir.
that. So that will give you the experience of what all one has to go through in order to just point the telescope to the right place. Don't you think that's important?
Yes, sir.
If you see, lots of things by our eye, we are fooled because lots of computations have already been taken care. So when somebody says, oh, that star which is now on the square, apparently that constellation is like a square, the bottommost or northmost or southmost corner, that star, then you can immediately follow that, no? So, but when you want to turn the telescope to that direction, the telescope will understand only azimuth and elevation, or if it is equatorial mounted, it will understand hour angle and declination. You have to give it that right hour angle, right declination, right, and so on. So I think that will be a good exercise. What else is? So the other thing is, it's also good to think about, do we really have to steer the telescope? Is there any other way, right? That will come back later, right? So yeah, I think that's essentially, so this is about next lecture, let's not worry about it. So there I stop. I think we have run out of time also, I think. Yeah, we're close. That's good. So I'll wait for some questions and any other discussion if you guys have anything further to say. Any questions? Yeah, please go ahead, Viren.
Yeah, so talking about these radio telescopes and even for optical, while I mean, of course, if it's a point source, it won't matter, but would we also need to consider the field of view while tracking a certain object? Because then we won't need to exactly get it to the center in case of radio telescopes also, right? Save a few seconds.
Yeah, so far I have not particularly talked about radio telescopes, right? It's generally about telescopes. And I have also included field of view. Essentially, it is mostly optical telescopes. We will come to actually the radio telescope and difference between radio and optical. Primary difference is that radio telescopes are not, they don't have field of view, in the sense that it's a single pixel receiving setup. Of course, more modern ones are becoming equipped with, let's say, 30 pixel or 100 pixels max, like that, right? But still, it is much smaller compared to an optical telescope. Optical telescopes have, let's say, a million pixels or even 10 million pixel CCD cameras, right? So which means 1000 pixels by 1000 pixels on a side. Even if you say that, because they do build in some amount of redundancy, so one resolution element will, let's say, occupy 2 by 2. So even then, it is 500 by 500 resolution element measurement simultaneous, which is quarter million measurements at one go, right? So they have so the resolution, so if it is, let's say that 500 on a side, the resolution, let's say, is say 1 arc second. So which means 500 arc seconds by 500 arc seconds is what, or let's say take it as 600 arc seconds. That means 10 arc minutes by 10 arc minutes simultaneous imaging is what is being done with the optical telescope. But radio telescopes, first of all, getting that resolution 1 arc seconds, that means that you have to really have a big dish. So the radio astronomers achieve the same kind of the resolution aspect in a different way. We'll come to that later. That is in the next lecture. In fact, that's there as part of my list of things that I will discuss. So the number one difference would be that the resolution element for a single dish in radio would be much bigger compared to optical. Optical is, let's say, 1 arc second. Of course, this is not diffraction limit. This is because of seeing limit. Those things, if we want to know about, we will discuss in the next lecture or later also. But basically, so if it is 1 arc second resolution, and then you have 500, 600, 10 arc minute by 10 arc minute imaging capacity. In the case of single dish radios, typically it will be maybe 1 arc minute or half arc minute would be the resolution element. Sometimes even worse. As you come to lower and lower frequencies, it can be even half a degree, right? For example, a single antenna of GMRT will have a half a degree or quarter degree resolution. How much is that? Lambda by? Yeah, I think it's quarter degree. So it's 20 centimeters, that is 0.2 meters divided by, let's say 40. So 1 over 200, yeah, roughly quarter degree. No, 60 by 240 would make it quarter. So maybe 1/3, something like that. So that is assuming the entire 45 meters, but it may not be entire 45 meters, which is illuminating at 21 centimeters, and therefore it will become slightly worse in the sense maybe half a degree. So that is the resolving element. That's a resolution. Below half a degree, the angle subtended by two objects come below half a degree. This guy will assume it to be a single object and give you one number in terms of its brightness or whatever, right? So then only by putting multiple receivers that we can have a wider field of view, but putting multiple pixels. So yeah, this is what in the next lecture we will deal with, the sense that optical telescopes are optimized for field of view, that they have, whereas radio telescopes have not bothered about it simply because that question itself didn't arise for a long time. Only in the recent past, people are thinking about equipping wider field of view cameras in radio telescopes, and therefore then worry about. So this optimization and all that we'll talk about. There are various types of telescopes, optical telescopes, where they have optimized for field of view. How they have done, all that we will discuss next lecture.
Yeah. I think, sir, it would mostly deal with the beam width, right? What the telescope is actually able to see, rather than.
If you are talking, okay, you may be having in mind interferometry. So in the case of interferometry,
even for a single.
No. In the case of single dish, yes, that resolution element is the beam size, and that's it. Below the beam size, you don't have a resolution, right? In the sense, the ability to find details below the resolution limit. But then you can actually resolve that out using multiple dishes. That is what interferometry does. There, the field of view corresponds to the resolution, single dish resolution size. We will talk about it in the next lectures.
Okay, sir. Thank you.
Now, let's focus on. Yeah.
Biswajit is asking a question, Biswajit. It is believed that at every 26,000 years, the axis of Earth gets tilted. Does these effects are present theoretical calculation of the great circle in pointing a location will shift by certain degrees?
Okay, so this is the precision of equinoxes. In the sense, even Newton had computed what the. So what happens is that, see, we can see my. Okay, let me assume that this is a plane, right? So this plane has a normal, right? This is a plane which is describing the equator of the Earth. But this plane, if it simply rotates like that, yes, then this plane will cross the ecliptic, that is the orbital plane, at 2 points. That's the equinoxes, right? But then if this plane itself is wobbly, right, then those points, equinoxes, will move, and that's what was determined long time ago. And then explanation was given as to why it's not stable. And then they computed the precession and nutation components. In fact, I think it was very early understood that this precession, that is this wobbling, is caused by interaction with sun and interaction with moon, these two components. I think, if I remember right, Newton calculated them, but not very accurately, but that was later on improved by Bradley, Hadley, or something like that later on. But
Okay,
yes.
sir. So what will be the effect of precision on RA index?
Okay. Okay. Can you imagine this? Let me describe this. Whatever I imagine, try and imagine the same thing. Okay. Imagine that there are two spheres. One is inside, another is just outside, very close. Now, initially, let's say that these two spheres will have an axis, right? Let's align this axis. Yeah. So then, if you have set of points on the inner sphere, and then you project them onto the outer sphere, they will all be at exactly similar positions, in the sense angular positions, as the inner sphere, right? But now, so the inner sphere axis is like this. The outer sphere's axis, I have tilted it with respect to the inner sphere. Okay. So now the inner sphere has these objects on its surface, which are projected onto the outer sphere. You will see that their angular positions are not the same as with respect to the inner sphere's angle. Correct? Do you follow what I'm saying up to this point?
Yes, sir.
Yes, sir. Yes.
But now this, with respect to the axis of the inner sphere, the outer sphere's axis is different, which meant that, okay, there is you have to map every point on the inner sphere to a new point on the outer sphere. That is just this rotation. You can compensate for that, you will get that. But this rotation, this mismatch in the angle is not also time constant. It's not constant with time. It keeps doing this. Okay, you follow? So at different times, the mapping has to be different, because with respect to the inner sphere, the outer sphere's axis is wobbling, is doing the wobble, right? And not only is it doing the wobble, but it is actually doing wobble, nodding over wobble, right? So yeah, it is a little, that is the reason why all these times are required. That is what is this periodicity of this rotation is 25,722 or whatever it is, approximately 26,000 years, right? So 26,000 years, it completes one circle. And within that 26,000 years, every 18.6 years, it is actually doing this jalebi. Okay. And therefore, and that amplitude is about 9 arcseconds or something like that. It's not much, but nonetheless, when you're talking about 1 arcsecond positional accuracy or 0.1 arcsecond positional accuracy, then these things become important, relevant. Yeah. So yeah, basically these things, it's a coordinate transformation. Basically, the inner, whatever I said as the inner coordinate, is the ideal celestial sphere, so to speak. All objects are projected onto the celestial. There, they will not change, right? But then the actual celestial sphere is doing this wobble, and therefore, depending on the time where you are pointing, this mapping, remapping should be done differently. So that's essential, and therefore, it is in this actual coordinate system you are measuring your alpha and dec. So that is the current alpha and dec. That is the precision and nutation correction that you have to do. I hope it's understandable.
Yes, sir. Yes, sir. Thank you so much.
Sir, Sanket has raised his hand.
Yeah.
Yeah.
Go ahead, Sanket.
Yeah, my question is kind of continuation with the previous question. So due to the precision, we need to change the equatorial coordinates somewhat. So like we had B names of pulsars a few years ago, and now we use the J names for the pulsars as the coordinate system we have changed slightly. So how oftenly we need to change these names, or the we need to update the coordinate system accordingly to use the new coordinates so that it won't affect much while doing practical observation.
Yeah. See, the reason, I mean, typically 50 years is considered as a good baseline for which these errors don't accumulate too much. Although I said that yes, it is 25,722. How do you know it is exactly accurate to 1 day? the phase of these vibrations, oscillations need not actually close, right? Although there are such errors. So this epoch, when they create a new epoch, this is done by positional astronomy and stuff like that. So they actually do a lot more corrections than what we have so far discussed, and then create the new epoch of, the coordinate system in which, right? So it's always good idea to use the nearest epoch and then do the precision and nutation correction, because you will make less errors. And every 50 years is considered good enough as of now for presenting this epoch coordinates. It may change if suppose the kind of demands become more in terms of precision and all that stuff. People might consider even much lesser time, every 10 years, 20 years or something like that. But right now, yeah, 50 years is considered reasonable.
Okay, sir, there is a question by Avantika. Does precision and nutation motion affect large telescopes which are mounted using an azimuth system?
No. This is nothing to do with the telescope. This is to do with okay, how do I say this? Which is what we have described, but I understand that this is a little bit you have to get it right. See, don't have a earth object like that. See, basically what it is saying is that you can imagine a sphere, Avantika. So this sphere has it's a rotating sphere, right? So it has an axis. So there is this axis, and then there is so there is angle about this axis, and then angle about from this plane. You can take longitudes and latitudes. So now, basically, what RA index is nothing but longitudes and latitudes in the celestial sphere of the objects. The problem is, so there is. I looked at them at one particular time and then took a snapshot of it and then populated the surface and say, haha, great. But that time, my axis of rotation, because the celestial sphere is defined by equatorial plane. Equator is Earth, right? So equatorial plane and the normal to the equatorial plane. So that the Earth's rotation axis at the time was pointing to, in the absolute reference frame, pointing to one particular direction. But that is not always the same because of the precision and nutation. So when this guy took the snapshot and gave me these coordinates, from then to now, my shaft, that is this equatorial, because even today I am defining my equatorial coordinate system only with respect to my equator, but my equator has changed because of the precision of the axis. And therefore, if I simply adopt those coordinates to be present in the present epoch also, I'll make error, gross error, because this particularly the precision is of the order of few degrees. So that means the object would have moved much away from where that person was without the correction. Nutation correction, it's only about 9 arc seconds or 10 arc seconds, or plus or minus 9. So 18 arc seconds maximum error can be. But yeah, that's, I hope you understand. It has nothing to do with.
Okay, yeah, I got that it will affect the area and declination of the celestial objects for sure. But I actually wanted to know whether it will affect the tracking system of the observatories or the large telescopes. in practical sense.
Okay. So, okay. Then if you're, look, what it means is the following. As long as you have computed the alpha and dec to the present epoch correctly, then equatorial coordinate system will give you the benefit because it's compensating only for the Earth's rotation. And since its axis should be aligned always to the Earth's rotation axis, right? So if the rotation axis changes, this axis also has changed, no problem. It's always, so therefore it will compensate for the Earth's rotation perfectly. So it is easy in the sense, for a celestial object, tracking will be concentrate in about one axis. That there is no issue, right? So always that benefit is there for equatorial coordinate systems. The only question is, are you pointing to the right direction or not? That is important, and that is what this precision and mutation has to ensure. If you are pointing to a wrong direction, yes, you will be compensating for the Earth's rotation correctly, no problem.
Yeah,
you will not see the
so
object.
it will be like it will be error free for say one epoch of time.
Yes, if supposing that it is not 2022 but it is 2050, and then people have produced a new not B, J, maybe G something, G 2050 coordinate system, and if you use that coordinates, you will see that you are not making any error, because its precision has to wait for another 18 years at least before the small corrections start playing a role. Another hopefully, well, the precision corrections, because it's 2 degrees, it may start mattering much more quickly. I'm not sure.
Oh, okay.
But within a couple of years, it should not be a problem. You may, even if you don't precise it, you may get the object right.
Yeah, right. Got it. Thank you, sir.
So, any more questions? There is one more.
Viren is raising the hand.
Yeah, hello.
Yeah, go ahead.
Yeah, sir, for mounts, basically, if they are automatic or even semi-automatic, we would require to calibrate it with some kind of a reference point. Usually, what type of reference points would we use, seeing that there is a certain change happening around the celestial objects?
So that I'm not sure I understand your question right, but basically the pointing model, right, includes all those errors. So, I mean, you are talking about calibration. So see, it's about the assumptions that we make and how much away we are from that assumption, and therefore we compensate for that. For example, azimuth axis tilt, elevation axis tilt, azimuth latitude, longitude error, time error, all kinds of things are included in order to, so for example, supposing, so here is the Earth, I am supposed to be local normal 1 degree, I have moved this way, let's say, then that is equivalent to a place which is 1 degree in latitude to the, say, south or north or whatever appropriately, right? So that is the latitude correction. Similarly, suppose there is a tilt like that, then that can be used as a, compensated by longitude or time correction. Then, yeah, the elevation axis tilt has more complex. You have to include certain terms for that. That's not quite easy to see. This tilt, what it will do, azimuth axis tilt, even though you are able to compensate in terms of, but it will create elevation axis tilt is the one which will create a cone of avoidance. You will never be able to reach certain points on your celestial hemisphere because this axis is tilted. So no matter how you rotate this, you will always go past a certain angle. No? Well, anyway, those things we can only, yeah, when those of you who may be actually doing this practical project, that time I can explain to you much more easily on piece of book, on a board and so on and so forth. In this format, I find it quite a little bit difficult to explain. Oh, I can try this. All right. So let me see. Oh, yeah. So are you able to? I have to stop share. Then I'll be able to. Somebody has to put the spotlight on me or something like that. See, what? Yeah, good. See, what it means is the following. So, ideally speaking, so this is a telescope. So it can rotate about this axis. It can rotate about that axis, right? So this is called. Do you guys see?
Yes. Yes.
So this
Yes,
is
sir.
yeah. So this is azimuth axis, and this is elevation axis. So the assumption that we make is that this is a perfect 90 degree. Now, practically, when you construct things like that, you will not be able to make it exactly 90 degrees. So what can happen? I'm going to exaggerate. So let's say that I'm. Okay, do you see this? So this is local normal. Let's say that azimuth axis, I've got it exactly perpendicular, but the elevation axis is not perpendicular. Okay, it is 90 minus some alpha. One side 90 minus alpha, another side 90 plus alpha, right? Yeah. Do you follow? So then you imagine if you rotate it about this axis, right? It will form a great circle, but not for. I mean, it will connect the south pole and north pole, but it will never go through the zenith. It will be offset by the same angle away from the zenith. Do you follow that?
Yes. Yes.
Yeah. So then, if you rotate it about this axis, you will see everywhere. I mean, from this. So like this, all your great circles will be going along a tangent to about a circle, but it will never be able to reach these points. About the zenith, your zenith is here. Yeah.
Yes.
You can imagine that, no? Yeah. So that means there is a cone of avoidance. There is a cone of solid angle that we cannot reach because of this elevation axis tilt. So those are all practical things you have to include. So as long as the object is outside this cone of avoidance angle, then you can point to them. So, but how do I calculate that? Even you can calculate those when it is in the cone of avoidance, you can find out, provided you have the so-called model, correct pointing model. If you have, you will be able to correct for all that. We'll go back to the screen share, is it? So, yeah, any other questions? Whatever I shared, is it reasonably clear and understandable?
Yes, sir.
Yes,
I
sir.
think there are no more questions.
Okay, please go ahead. There are more questions, fine. See, I'm also trying to answer it as much as I can in terms of clarity, but I hope that it is helping you. Any further questions? Otherwise, we can next time that we meet, we can start with your unresolved questions if there are any, and then go to our actual lecture. Is that okay?
Yes, sir.
You can think about it And also in the process of this assignment, trying to answer the assignment, you will come across lots of things which, I may have mentioned it now, but then you will find it difficult to understand or something like that. That's also fine. We'll then resolve that. Okay.
Yes.
So do we call it a day? How is it done?
So, sir, thank you for joining, and it was a really good explanation to you today. And if there are no more doubts, we can end the class today.
Yeah. If nobody has raised their hands as of now, isn't it? And
Yes, sir.
if any of you have some doubts, fine. You ponder about it, think about it yourself, and then next time we meet, we can certainly take them up first before we start the class. Is that okay?
Yes, sir. Thank you. Thank you all for